In this video, we're going to be looking at Chapter 17, Section 2, and we'll be talking about buffer solutions. And buffer solutions are incredibly useful. There's lots and lots of applications for them. We'll start here talking about what a buffer solution is, what it entails. It has to have a combination of a weak acid and its conjugate base in solution. And both of them need to be there in significant amounts, typically at least 10 to the negative 3 molar or more. And even at 10 to the negative 3, we're not talking about something with a very high buffer capacity. So we need to have a significantly high concentration of both the weak acid and its conjugate base at the same time. Over here on the right side of this, you'll see that there are several buffer solutions that are represented. We've got one that is at pH of 7, a pH of 10, and a pH of 4. Although you can get one that is at just about any pH that you're looking to create. There are lots of possibilities, and we're going to talk about how it is that we go about picking the things for a particular buffer. So we want to look at how it is that we go about making a buffer. We know that it has to have both the weak acid and the conjugate base present in order to have a buffer, but there's a couple of different ways that we can achieve that. One is simply to mix a weak acid and the salt of the conjugate base together, and that will make a buffer. And probably the simplest one, and one that would be the easiest to make, would be acetic acid and sodium acetate. We saw two buffers that were similar and related to this on number 15 and number 13 on the in-class assignment. And in fact, we're going to come back to number 13 here in just a couple of minutes. So acetic acid and sodium acetate, if you just mix those together, you will get a buffer solution. Of course, it has to be in water. You can also take a weak base and the salt of its conjugate acid. And so an example would be ammonia. And if you have ammonium chloride, which is the ionic compound, when you take ammonia with HCl, you'll get ammonium chloride. Well, if you take equal parts of ammonia and ammonium chloride, you are going to have a buffer. And so that is a possibility as well. Another possibility is to add enough of a strong base to a solution of a weak acid to partially neutralize that weak acid. You don't want to 100% neutralize it, because then you won't have a buffer solution anymore. Remember, you have to have both the weak acid and the conjugate base. So here is an example. If you take 0.050 moles of sodium hydroxide and add it to a solution that has 0.100 moles of acetic acid, that will create a buffer. In fact, that buffer will have the same pH as the one if you had equal amounts of acetic acid and sodium acetate to begin with. And then finally, a fourth way to do it is to come at it from the other direction, add enough of a strong acid to a solution of a weak base to partially neutralize that weak base. And I'm using the same math here, but if we add 0.050 moles of HCl to a solution that has 0.100 moles of ammonia, that will also give us a buffer. So those are all ways to make a buffer. Now what we want to do is we want to look at how a buffer works. Well, in order for it to be a buffer, and the whole point behind a buffer is that it's resistant to changes in pH, in order for it to be a buffer, it needs to be able to absorb a significant amount of either a strong acid or a strong base without messing up the pH very much. And the way that you can do that is to have enough of the weak acid and the conjugate base present, so that if a strong acid is added to it, there's still some of each left. So here is an example. If we have a solution that has 0.100 moles of HF and 0.100 moles of fluoride ion, and we come along and add 0.010 moles of a strong acid. Now that strong acid could be something like hydrochloric acid or nitric acid or any number of acids. Hydrochloric would probably be the best choice just because there's fewer side reactions. But if we add something like hydrochloric acid to the fluoride ion, it will react with the fluoride ion, or we add it to the buffer, it will react with the fluoride ion, and it will convert some of that fluoride into hydrofluoric acid. So the constant, or the amount, the number of moles of fluoride would decrease, and the number of moles of HF would increase. But the key feature here is that there's still some of each left. As long as there's some of each left, it is still a buffer. Now, the pH of the solution here is going to be a little bit lower than the pH of the solution here, but it's still going to be pretty close to that buffer, the pH of your initial buffer. By the way, in case you're wondering, this is a horrible buffer. It would be dreadfully toxic to have hydrofluoric acid. Just in case you were thinking of making your own buffer at home, make it with acetic acid. Don't make it with hydrofluoric acid. All right, so here's another possibility. Here we've got a buffer that, again, it's the same amounts, 0.1 moles of both HF and the fluoride ion to start with, but this time we're adding a strong base to it by adding 0.010 moles of hydroxide ion, presumably in the form of something like sodium hydroxide. We could neutralize some of that HF and convert it into fluoride ion. So the concentration, or rather the amount of HF would decrease and the amount of the fluoride ion would increase, but because we still have some of each present, it would still be a buffer. Now, the pH of this buffer would be somewhat higher, a few tenths or a few hundredths of a pH point higher, but it would still be pretty darn close to the pH of your original solution. So that is how a buffer works. It has to have some left. If there's not some left, it's not going to work. We want to look at buffer calculations. And so if we've got a weak acid, we know that we can write out the equilibrium reaction for that. And we've seen something like this multiple times, so I'm not going to explain that. And we know that we can write out the equilibrium constant expression, the Ka expression, or the acid dissociation constant expression. So hydronium times the conjugate base concentration divided by the concentration of the weak acid. Well, with that equation, we can do a little bit of math. And that little bit of math is this, that we can take the negative log of both sides of the equation. And when we take the negative log of Ka, we'll get this. And if we take the negative log of this product, so hydronium times A minus over HA, we can split that out. As the negative log of the hydronium ion concentration plus the negative log of this ratio, concentration of the conjugate base over the concentration of the acid. Well, this is the pKa, and this is the pH, and we're going to rearrange this so that we're going to solve this for pH. So when we solve that equation for pH, that's the negative log of the hydronium ion concentration, and then here is negative log of Ka plus the log of the concentration of our base, our conjugate base over our weak acid. And now in place of this, we're going to put pH, and in place of this, we're going to put pKa. Well, this is called the Henderson-Hasselbalch equation. And when we use the Henderson-Hasselbalch equation, one of the things that we can do is we can, in place of these concentrations, rather than put equilibrium concentrations, we can put initial concentrations. In doing so, though, we are assuming that it was okay to neglect X when we did our calculations. Let me explain. We're going to go back to number 13, and I've got it here on my document camera, number 13. And I've written the Henderson-Hasselbalch equation in terms of this particular reaction. So this one is, as you might recall from a little while ago, is propionic acid plus water gives us hydronium plus the propionate ion. And we had some of the propionic acid and some of the propionate ion, and we went through and remember, since we had some of each, we were able to neglect X both in the numerator and the denominator, and we were able to come up with a value of 4.73 for the pH of that particular solution. Well, we can use those initial values and put them into this expression. So pKa is equal to the negative log of, let's see, our Ka was 1.3 times 10 to the negative 5 plus the log, and our concentration of the propionate ion was 0.060. And our concentration of the propionic acid is 0.085. In putting those numbers in there, we are assuming that it's okay to neglect X. That is essentially what we're assuming. That also means that we can really only use this Henderson-Hasselbalch equation on buffer solutions. So let's put the numbers in to our calculator. Let me make sure I get that over here. All right, we'll clear all that out. And so we'll do the negative log of 1.3. So negative log of 1.3 times 10 to the negative 5. All right, plus the log, and we'll do 0.06 divided by 0.085 in closed parentheses. And so that's going to give us that particular section, and that will give us, and if you look at that number, we get 4.73. And in fact, if you look, the numbers here are even the same. If you were to compare that to the numbers we had looked at previously when we did this calculation. What that tells us is this calculation is doing exactly the same thing as writing all of this out, but we use a lot less space. And that's why we like the Henderson-Hasselbalch equation. So that is why we like the Henderson-Hasselbalch equation. So let's look at an example of Henderson-Hasselbalch equation. And then we'll do a couple more problems on Henderson-Hasselbalch on the in-class assignment. All right, so using the Henderson-Hasselbalch equation, here is an example. What is the pH? So we're looking for the pH of a buffer that is 0.12 molar in lactic acid and 0.10 molar in sodium lactate. Well, here it's really a matter of identifying what our acid and what our base are. Our acid is the HC3H5O3, the lactic acid, and our base, the conjugate base, is the C3H5O3. Sodium ends up being a spectator here. Sodium doesn't affect the pH. And then here is the Ka. Normally you would have to go look that up in the appendix D1, but here we don't need to. So here is our pH. pH is equal to pKa plus log of the concentration of our conjugate base over the concentration of our weak acid. And now we'll just put those numbers in. So negative log of 1.4 times 10 to the negative 4. Our base was 0.10 molar, and our acid was 0.12 molar. When we put those in, we are going to end up with, you'll see this number is negative because if you have log of 1 is 0. And if this ratio is less than 1, you're going to get a negative component here. If this ratio is greater than 1, you will have a positive component there. But it comes out a little bit negative there. And you'll see we get the number 3.77. So that is the pH of that particular buffer. So we're going to go look at numbers 20 and 23. Let's start off here with number 20. So calculate the pH of a buffer that is 0.120 molar in sodium bicarbonate and 0.105 molar in sodium carbonate. Well, to solve this, we need to recognize, first of all, what is the weak acid and what is the conjugate base. Our weak acid here is going to be the bicarbonate ion, and our base, the conjugate base, is going to be carbonate. So when we write this out as our Henderson-Hasselbalch equation, we'll get pH is equal to the pKa plus the log of the concentration of carbonate, CO3 divided by the concentration of bicarbonate. Okay. And now we want to put the numbers into this equation. Well, we'll need to get the negative log of the Ka, and so we'll have to look up the value for Ka for bicarbonate. So I'm going to flip back over here and go to Appendix D1. And you'll see here on Appendix D1, we've got carbonic acid. Carbonic acid, the Ka1, that's not the one we want. We want the one for bicarbonate, which is Ka2, and that is 5.6 times 10 to the negative 11. So I'm going to put negative log of 5.6 times 10 to the negative 11. And I'm going to tab back over here. All right, so there we go. We've got that, and then plus the log. And for carbonate, we'll have 0.105, and for bicarbonate, 0.120. Again, you'll notice here that this number is less than 1, which means that's going to be a negative component of this. So we'll go ahead and do our calculation. So negative log of 5.6 times 10 to the negative 11. Left out a 1 there. All right, so 10 to the negative 11 plus the log of 0.105 divided by 0.120. All right, and that will give us the entire quantity. That comes out to 10.19. So 10.19. All right, so that was pretty easy. And so now what we want to do is let's do part B. On part B, it says calculate the pH of a solution formed by mixing these two solutions. So 85 milliliters of 0.2 molar bicarbonate and 65 milliliters of 0.15 molar carbonate. Well, we're going to need to calculate the concentration of bicarbonate and carbonate and put them into the equation. We'll start with bicarbonate because it is listed first. So our concentration of bicarbonate is going to be equal to 85.0 milliliters times 0.200 molar divided by the total volume, which is 85 plus 65. So 85.0 milliliters plus 65.0 milliliters. And the quantity that comes out to, so 85 times 0.2, and then we're going to divide that by 85 plus 65 in closed parentheses, and we will get 0.113 molar. Now for carbonate ion, CO3 2 minus. So CO3 2 minus, and we will have 65 milliliters times 0.150 molar, and we will divide that by, again, 85.0 milliliters plus 65.0 milliliters. And then that is going to give us a different quantity. So let's get that number. So 65 times 0.15, and then we will divide that by the sum of 85 plus 65. And that gives us 0.0650 molar. We do have 3 sig figs, so I'll leave that as 3 sig figs. All right, well now we'll use our formula. So pH is equal to the pKa. So pKa is the negative log of 5.6 times 10 to the negative 11 plus the log of the concentration. Here, they got off the page there a little bit. Concentration of carbonate, so log of carbonate, which is 0.0650. And bicarbonate, which is down here in the denominator, is going to be 0.113 molar. All right, we'll clear all that up, and we will put negative log 5.6, 10 to the negative 11, plus the log of 0.065 divided by 0.113. And you'll see the number that we come up with is 10.01. So that is our pH. If you are ever in a pinch and you want to create a buffer solution in your own household that is a pH of 10 approximately, you can take approximately these ratios of carbonate and bicarbonate. Bicarbonate is just baking soda, and carbonate is washing soda. And you can purchase those things at the grocery store, and you can create your own buffer solution at your own home that has a pH of 10. And I don't know how many times I've said, I really, really wish I had a buffer solution of pH 10 out of household objects. I'm sure you'll be saying that anytime now. Okay, so on this next one, how many moles of sodium hypobromite should be added to 1 liter of a 0.050 molar hypobromous acid to form a buffer solution of 9.15? Assume that no volume change occurs when we add the sodium hypobromite. All right, this is a situation where we're trying to determine how much of the sodium hypobromite to add. So in terms of our equation, so pH is equal to the pKa plus the log of the concentration of BRO minus over the concentration of HBRO. Well, the quantities that we know are the pH, so we know that quantity, the pKa, which we don't know directly, but we can get that. So we're going to get that here. Let's go ahead and go over here. We'll find hypobromous acid, and there is hypobromous acid at 2.5 times 10 to the negative 9. So I'm going to write that down. Ka is 2.5 times 10 to the negative 9. I'm going to make sure I wrote down the right number. Yes, so 2.5 times 10 to the negative 9. All right, so there is our Ka, and so we can calculate pKa really, really easily. And then, of course, HBRO is 0.050 molar, and we want to solve this equation for BRO minus. So let's do pH is 9.15. pKa is the negative log of 2.5 times 10 to the negative 9 plus the log of the concentration of BRO minus over 0.050 molar. All right, we need to get a quantity here, so we're going to calculate what that is. So negative log of 2.5 times 10 to the negative 9, and that gives us 8.60. So 9.15 is equal to 8.60 plus the log of the concentration of BRO minus over 0.050. Well, now we'll combine these two terms. So we're going to subtract 8.60 from both sides. So 9.15 minus 8.60, and that gives us 0.55. So I'm going to switch the equation around. I'm going to write it this way. Log of the concentration of BRO minus over 0.050 is equal to 0.55. Now that we have that, we're going to take the inverse log or the anti-log of both sides. Since it's log base 10, that means we're raising it to the 10th power. So we'll get concentration of BRO minus over 0.050 is equal to 10 to the 0.55. Since we're really close here, before I evaluate that number, I am just going to cross multiply and get us this, that the concentration of BRO minus is 0.050 molar times 10 raised to the 0.55. Now we can't use the EE button on this. We're going to have to just put 10 caret 0.55 to make this work. So I'll do 10 raised to the 0.55, and we get that quantity. And then we are going to multiply that by 0.050, and that's going to give us this amount. So we'll get a concentration of BRO minus that is equal to 0.177 molar. Now, as far as limitations here, we really only have 2 sig figs, so I'm going to go ahead and round that to 0.18 molar. We do have one last little thing to do, and that is because it asks for moles, not just the concentration, we're going to multiply that molarity times 1 liter. It doesn't change the number. We won't need a calculator at this point, but 0.18 moles per liter times 1.00 liters gives us 0.18 moles of hypobromite. And we're adding it in the form of sodium hypobromite, so I'm going to put NaBrO. Okay, well, that is our buffer calculations. Now, before we finish up this section, there's a couple of other little details that I want to show you guys before we move on to talking about titrations. So let's switch back over to the presentation. And we're going to look at something that we refer to as buffer capacity. And buffer capacity it's how much acid or base you can add to a buffer before the pH starts to change by a significant amount. And so, like, if you have very small quantities of your weak acid and your conjugate base, your buffer capacity is going to be pretty low. But if you have higher concentrations of your weak acid and conjugate base, your buffer capacity is going to be high. So the bigger these numbers are, the higher the buffer capacity is going to be. And it turns out if you've got 1 molar and 1 molar, that's going to have the same pH as if you had 0.1 molar and 0.1 molar. And the reason for that is that this is a ratio. So if this is 1 to 1, that's a ratio of 1. Log of 1 is 0. If you had 0.1 and 0.1, well, that's still log of 1. The only time this really becomes an issue where you can't just do that is if these concentrations get so low that it's not okay to neglect X, like we did back in problem number 13. If it's not okay to neglect X, then we start to get into some issues. But again, you have to get pretty low concentrations for that to occur. So we'll find that the larger the values of these concentrations, the larger the buffer capacity. And this is the note. Small values for the concentrations, and by that I mean less than 0.001 molar. It makes the Henderson-Hasselbalch equation less reliable. And so, you know, if we're going to have a buffer solution, we need to have a significant amount of these. Another topic that we want to look at is something that we refer to as the pH range. And pH range is the range of pH values over which a buffer works effectively. All right. So if we consider a situation like this, where our concentration of our weak acid is equal to the concentration of our conjugate base, which is equal to some number, and I'm just going to say 0.10, that means that when we put that into the equation, your pH is equal to the pKa plus the log of 0.1 over 0.1. Well, 0.1 divided by 0.1 is 1. And if you look, I encourage you to do this in your calculator. Go in and do log of 1, and you will find that that comes out to 0. And if you do the log of 0.1, you will see it comes out to -1. And if you do the log of 10, you'll see that that comes out to 1. And so really this is how much does it affect the pH away from the pKa. And so again, if this is a 1-to-1 ratio, then that means that log of 1 is going to be 0 and that the pH will be equal to the pKa. So the pH will be equal to the pKa. We'll find that the effective range for most buffer solutions is going to be about plus or minus 1 pH unit from the pKa. And so if, as I mentioned, if your concentration of base, the ratio of your base to acid is 0.1, then you're going to have, it'll be, your pH will be 1 pKa or 1 pH unit less than the pKa. If your ratio here is 10-to-1, then your pH will be plus or minus, your pH will be 1 pH unit greater. So that means if we're looking for a particular pH, then we can go look for an acid that has a pKa close to that pH. So we can look for one that has a pKa close to that pH. All right. Well, now we want to look at the pH of a buffer solution after we add some strong acid or strong base to that solution. And there's a couple of steps that we use when doing these kinds of calculations. The very first step is determine which reaction is going to occur. And this is pretty easy. If you're adding a strong acid, then the strong acid will neutralize some of the weak base. And it will convert that weak base into the weak acid. If, on the other hand, you're adding the strong base, you're going to be neutralizing some of the weak acid and converting it into the weak base. So again, if you're adding strong acid, you'll neutralize some of your weak base. And if you add the strong base, you'll neutralize some of your weak acid. Either way, we will need to do a calculation. And the kind of calculation that I do is I call it a before and after table. And the reason I call it a before and after table is to distinguish it from a concentration table. Concentration tables, we only use concentrations. In before and after tables, we use moles. So we'll use the before and after table, and that will determine the new number of moles of HA and A minus, so the weak acid and the conjugate base. Once we know those numbers of moles, we can calculate the new concentrations if need be. Sometimes we can just plug the moles in. I'll show you when we can do that here in a bit. And then once we have those numbers, we put that into our Henderson-Hasselbalch equation, provided that it's still a buffer, and then we can calculate the pH. So let me show you an example. So this is a buffer that we looked at way back in chapter 16, and we looked at it earlier in this presentation here in chapter 17. And it's a buffer that's made by having 0.300 moles of acetic acid, 0.300 moles of sodium acetate, and then it's diluted up until we get 1 liter of solution. Well, since we have 0.3 moles in 1 liter, it's 0.3 molar in this and 0.3 molar in this. So when we put that into our equation, pKa is the negative log of Ka, the log of the concentration of base over acid. So this is 0.3 divided by 0.3. 0.3 divided by 0.3, of course, is 1. Log of 1 is 0. So the pH at this point is 4.74. We want to see what happens when we come along and add either a strong acid to this or a strong base. If we add a strong acid, it's going to cause the pH to go down. But you'll see that the pH does not go down very much. If we add a strong base, the pH will go up. But again, it doesn't go up by a huge amount. And that's really the whole point behind buffers, is that the pH doesn't change very much. All right, so, I got some spoilers here. It tells you what the pH is going to be, but let's look at doing the calculation of a before and after table. So we're going to start with, I believe we're going to start with the adding the base, yes. So here is our buffer, 0.3 molar of this, 0.3 molar of this, has a pH of 4.74, as we just calculated a minute ago, and we calculated earlier and in chapter 16. We want to calculate the pH after adding 0.020 moles of sodium hydroxide. So we're going to add a strong base. Well, first thing we want to figure out is, what is the strong base going to react with? Well, of course, that strong base is going to react with our weak acid. So this is the reaction that is going to occur. Our weak acid reacts with hydroxide, and it will create some acetate ion. So we're going to neutralize some of that acid and increase the concentration, or increase the number of moles of our conjugate base. So here is a before and after table. Again, the key difference between a before and after table and a concentration table or / ice table, ice tables have concentrations in them. Before and after tables have numbers of moles. So our numbers of moles of acetic acid and acetate were both 0.30. So acetic acid is our reactant, hydroxide is our reactant, and this is going to be a product. Here, if we add with the 0.300 moles of the acid and 0.020 moles of sodium hydroxide, we can clearly see that the limiting reactant here is going to be the hydroxide. So that means that all of our hydroxide is going to be used up. So that will go from 0.020 down to 0.000. Well, however much this decreases, this will increase. So this will also decrease rather. This will decrease by 0.020 moles, and we will end up with 0.280 moles of acetic acid. Well, that acetic acid, any acetic acid that we use up is going to produce some acetate ion. Because we're neutralizing it, we'll be creating some acetate ion. So the number of moles of acetate will increase from 0.300 moles up to 0.320 moles. Well, we're going to take those numbers and put them into our Henderson-Hasselbalch equation. So here is our Henderson-Hasselbalch equation. Here's our pKa, which is the negative log of Ka. We know that number was 4.74. And then here, because this is not an exactly even number, we have 0.32 and 0.280. And with those two numbers. When we put them in, you'll see that that gives us about 0.06. So our value goes up to 4.80. So 4.80. So by adding a pretty significant amount of sodium hydroxide to a liter of water with this other stuff in it, our pH only went up by 0.06. Not bad. Well, now let's look at the opposite situation. And instead of adding a strong base, we're going to add a strong acid. So here is our buffer. Again, we're starting back at the original 0.30 and 0.30 moles of the weak acid and the conjugate base. Our original pH, of course, was 4.74. We now want to calculate the pH after adding 0.020 moles of HCl. HCl is a strong acid, which means it dissociates 100%, and the chloride ion has no effect on the pH, so really all we care about is that we're adding H+. So we're going to be adding 0.020 moles of H+. Well, that strong acid is going to react with the conjugate base. It will react with the acetate ion. So we need to write down the reaction between H+ and this acetate ion. So there's our acetate plus the H+, and then here is the acetic acid. As far as what goes in our table, we've got 0.30 moles of our acetic acid, 0.300 moles of our sodium acetate, which we're just going to write acetate, and 0.020 moles of the hydrogen ion, because this is a strong acid. So here is what our before and after table looks like. Before, 0.300, 0.020, and 0.300. Since these are our two reactants, we look at those quantities. This is clearly the smaller number, so we're going to run out of this. That is our limiting reactant. We're going to run out of H+, so the concentration, or the number of moles of H+ will decrease by 0.020 moles, and we'll end up with no moles of H+. This is going to also decrease by 0.020, and that will give us 0.280. And then as far as the acetic acid goes, because we're neutralizing some of that conjugate base, we're going to be increasing the number of moles of the acetic acid. It will go up by 0.020 moles, and we'll end up with 0.320 moles. Well, now we can plug these numbers into our Henderson-Hasselbalch equation. And so here we've got 0.280 moles for the acetate, so that one goes up in the numerator, and 0.320 moles of the acetic acid, that one goes down in the denominator. And so here we've got the pKa, and you'll see that the number becomes 4.68. Well, you'll note that it was 4.74, and even with adding a pretty significant amount of a strong acid, the pH only went down by 0.06 pH units. Not bad. Not bad at all. All right. Well, we're going to stop the video here, and this is the end of section 17.2, and our next video is going to be our last video of the content for exam 3. And that content, and again, that'll be section 17.3, and it's a pretty challenging section, so you may want to watch that video twice. So